We're Math 30. This is lesson 5, and this is where we dive right into trig identities. We worked on trig expressions, and now we go into identities. The first question asks us, use the quotient identity to show. So if we look at this, we say, okay, well, I do an identity by keeping left side and right side separate. So sine x is equal to, in this case, tangent x is sine x over cos x, which is multiplied by cos x. I cancel, and therefore I can see that sine x is equal to sine x. Therefore, it's proven that those two are equal. But is this a true identity? If we investigate the graphs for sine x and for g at x equal to tangent cos x, look closely and see what you see. So as you can see, when you graph those two, you think you get exactly the same graph. But as we'll investigate a little deeper, let's look and see what each of these values are and see what you notice. So investigate what is f at pi over 2 and g at pi over 2, and in those values, see what the exact values of those are when you plug them into your calculator and see what you notice, okay? So when you actually do the work, you say, okay, at pi over 2 and at 3 pi over 2, one of them is 1, but the other one is and minus 1, but the other one is undefined. When you look closely, there are points of discontinuity at pi over 2 and at 3 pi over 2. And when you actually look at the graph of this graph looks like this, but it's really not quite that way. There is a hole right here and a hole right here. And the reason why is that when you actually look at the function g at x, yes, we have reduced it, but when we talked about rational expressions, g at x is really sine x times cosine x over sine x. And when we looked at rational expressions, they do simplify to give you, pardon me, I wrote the wrong expression down, but we have sine x over cos x times cos x. So if you cancel the cos x's out, you do get sine x, but you have to remember that you need to write the NPVs to start. And between 0 and 2 pi, the non-permissible values are that cosine x must not equal 0, and therefore x must not equal from 0 to 2 pi, pi over 2 and 3 pi over 2. And that's the reason why. The correct graph, as you can see, is the graph with the holes. And now as you ponder this, we say that sine x is an identity, but it has non-permissive values where cos x equals 0. The restrictions are pi over 2 plus n pi and n is non-integers. These holes, as it talks about here, may not appear in the calculator, but that doesn't mean they're not there. Your calculator is not nearly as smart as you are. You have to be aware of that. And again, it talks about how you could use your calculator to find the holes, but the reality is the algebra will set you free, and you need to be able to do that algebraically. All right? In the next page, it talks about the non-permissible values and defining what they are. Anytime that you have a quotient, that bottom cannot be equal to 0. So you have to be aware of non-permissible values anytime you have a quotient. So as you read through, obviously tangent and cotangent, those are all quotients, so that's why they have it. And number 2 really, as I think, is the key, that anytime that you have a denominator, that's the most important thing. Non-permissible values are sometimes called restrictions on the identity, and in many examples, restrictions to the solution. Sine x equals 0 or cos x equals 0, that's the important one, okay? There are some hints for following steps in identity. They're a little bit like what we've talked about before. So this is your procedure that kind of guides you to success. All right, so as we follow through, let's go and follow this procedure as we try some identities, right? Now, at least what's different about what we're doing today compared to last day is that we now at least have a plan. So I'm going to look at the left side and I say, okay, well, I've got 1 over cos x minus cos x, and I've got sine x times tangent x. And as I look at that, I say, well, which side is the simpler side? Sometimes you could work with both of them. All right, so it says verify. Okay, first off, we're supposed to verify this statement is true for pi over 3. So I plug in pi over 3, and 1 over cosine pi over 3 minus cos pi over 3. What is that equal to on this side? What is the cosine of pi over 3? That is 1 divided by the cosine of 60 degrees is 1/2 minus 1/2. That's equal to 2 minus 1/2, which is equal to 3/2. What's sine x times cos x? Well, what is the sine of pi over 3 times the tangent of pi over 3? Well, the sine of pi over 3 is root 3 over 2, and tangent of pi over 3 is equal to root 3, so that ends up being equal to 3 over 2. We can use a graphing calculator to show this statement is true as an identity. So we're looking to see, are they the same graph? So you look and say, are they the same graph, and see what they look like. So I want you to graph that on your calculator and see if they're the same. Proving the identity is true using an algebraic approach. So now we go to the procedure on the following page, or the preceding page. So 1 over cos x minus cos x equals sine x times, now I'm going to work with both sides. I know that tangent x is equal to sine x over cosine x. So if I look at this one, what do I get? I get sine squared over cos x. Can I make this side into the same thing? Well, I take this side and I use the common denominator, so I get 1. If I multiply top and bottom here by cos x and cos x, I end up with 1 minus cosine x squared all over cosine x. What is 1 minus cos squared? That is equal to sine squared. And therefore, left side is equal to right side. Proven. Okay. What are the restrictions on the variable? Well, where is our quotient? Our restrictions on the variable are where cosine x cannot equal 0. There we're back to our, well, that means that x cannot be equal to pi over 2 plus n pi, where n is an element of integers. Okay. Example 2. Prove the identity sine x times cos x squared plus sine cubed. So this one's a little bigger. Clearly, the easiest side is cosine x. Now that side is fairly simple, so there's nothing really to do there. 1 over cosine x, 1 over cosecant x, that would just be the reciprocal, right? Cosecant is 1 over sine, so if you took the reciprocal, this is actually just equal to sine x. So can we simplify that whole left side into something as beautiful as just sine x? Well, we've got some work to do because we're starting off with sine x cos x squared plus sine x cubed. So we've got some work to do. One of the things we could do, you notice that you could factor out the sine x. And if you do that, you simply get sine x times cos x squared plus sine x squared. And bada bing, bada boom, now you simply have sine x times 1. Therefore, left side equals right side. The key is following the procedures we talked about on the front page. Pick the easier side, use your Pythagorean identities, use the skills you've developed in factoring and so on over the grade 10 and 11, right? And follow through to a proof. Oh, determine the non-permissible values. We don't have any here because technically we have no quotient here. There is nothing in the bottom. Actually, I take that back. Non-permissible value, you have to be careful. If you look at this first step, this right here is actually 1 over sine x. So as much as when you simplify it, it's not a denominator, there is a denominator there. And so we do have a non-permissible value, and our non-permissible value turns out to be when sine x is equal to 0. And sine x is equal to 0 at x cannot, sine x cannot be equal to 0, so x cannot be equal to n pi, where n is an element of integers. Going to example 3. Bigger identity, we got sine a plus tangent a all over 1 plus cosine a is equal to 1 over kind. Prove the identity algebraically. Again, pick the nicer side. So again, you must start off by separating these two. It is not considered legal to have an equal sign because you don't know whether this is actually legal or not. So the right side is 1 over tangent of a, which we know is equal to simply tangent A. So can we make this other side into that? So what have I got? I've got sine A. Doesn't look like any kind of Pythagorean identity. Oopsie. We'll get rid of that. Sine A plus sine A over cosine A all over 1 plus cosine A. So we're not leaving us a lot of room to work with it here. But what we are going to do is we are going to look at this and say, well, I have a multi-level condo here, so I'm going to multiply the top by cosine, and I'll multiply the bottom by cosine, and let's see what we end up with here. If I multiply the top through, let's just see, sine A, sine over cosine A, 1 plus cosine A. So now we end up with, oops, that should be an A. Oops, I think we had a bit of a pause there. So now we multiply that through, and we end up with cosine A sine A plus sine A all over, in this case, I'm going to leave that cosine A out. Cosine A times 1 plus cosine A. The reason I leave it out is I look and I see, and again, this just takes practice, I look and I see what can I do with the numerator. I can factor out a sine A there, and when I do, I end up with sine A times cos A plus 1. And on the bottom, I've got cosine A times 1 plus cosine A. And we can clearly see that those two are equivalent. And now you end up with sine A over cos A, which is equal to tangent A, which therefore left side is equal to right side. So we're a little bit short of space there. And now we go back to the beginning and we look and see, what are my non-permissible values? Well, look and see where the denominators are. And I need to rewrite this one. This is 1 over sine A over cosine A, which could then be equal to, that's 1 over 1 over tangent A. So this would be cosine A over sine A, which would then be equal to sine A over cosine A. So in the process, you have to look and see, when are these things equal to 0? When is their bottoms? When are the denominators? What are the denominators in each of these expressions? Well, there's a few. When we look across, I see a cosine A in the bottom at one point. So cosine A cannot be equal to 0. I also see right here that at this point there's a sine A in the bottom. So sine A cannot be equal to 0. And for each of those, we need to have restrictions. We also see, when you look at this one, that 1 plus cosine A is in the bottom. And because of that, we also need to say that cosine A cannot be equal to -1. And so we need non-permissible values for each of those. All right, so those are the restrictions that you can see up there for the identity. And in part C, they ask you to do the non-permissible values and see why each of those non-permissible values exists for each of those functions. So in A, it's just showing you that this one is for cosine A cannot be equal to -1. So those are the places. And in this one, you have both of them, right? You have cosine not equal to 0 as well as sine not equal to 0. And so there's two sets of restrictions here. That's why there's more. All right, I'll let you finish example 4 and the assignment that you need to do there.